right, well, good morning, everybody. This is Jomo Stewart here at the Fairbanks Economic Development Corporation. We are here with Mr. Glenn Brady. Oh, whoa, we usually start with, here we go. It is Tuesday, December 12th, 8:05 in the a.m. And we are here for today's Energy for All Alaska Task Force. We have, in residence, actually, we have Miss Lisa Slava, my intrepid project manager, but we also have Mr. Roger Burgraff. Welcome, sir. Good to see you. It's been a little while. And our guest today is Mr. Glenn Brady, as well as some of the members of his team at PanAlaska LLC, here to brief the group on the Arctic Light, the innovative Arctic Light modular structural system. All right, can everybody see the share screen?
Yep, I got you, Jomo.
Perfect. All right, well, then we will get this show on the road. Mr. Brady.
All right. Well, you can do the deck for me, but welcome everybody, and nice to see folks online. My name is Glenn Brady, and online we've got Mark Sherman. He's the co-founder. Here in the room with me, we've got Dr. Jen Pickett, who's our industrial organizational psychologist. And as well online, we've got one of our developer, or the developer we're working with that we'll go into later, but that's Marshall James. So we're pleased to tell you about what we've got going on with Arctic Light and our manufacturing operation. So what Arctic Light is a kind of what we call a revolutionary approach. It's patented, or patent pending now, and this is manufactured locally. It's a light gauge steel framework encased in EPS foam. So it's a very different approach to how a thermal structural envelope is created and constructed. With the entire goal of being able to manufacture and build high quality, energy efficient housing with a much reduced labor skill set. Particularly in harsh environments that we all know about up here. So, all right, next, Jomo. So that's the who we are. Mark and I are both lifelong Alaskans and both engineers. Mark's the recovering consultant, and I'm still not smart enough to get out of business, so I still am leaned into this. I have listed in the who we are. I'm a member of the ALCOM Civilian Advisory Board, and I think there may be a couple of other folks online that might be a part of that group. But this project was originally conceived to address the critical housing shortage that was initially, related to the defense buildup at Eielson and the community's need to deliver housing and a lot of the challenges that the community was facing in doing that. So we took a different approach to try to address those issues. Go ahead and next slide, Jomo. So this is kind of a highlight of what we've done. The initial concept for this system was developed over 2 years ago. And in that time, we've taken some pretty significant steps and made some big milestones in terms of bringing this technology to commercial market. Up to most recently, we've done a structural testing of what we call tall wall panels. These were for a large commercial project where we were testing 24-foot tall wall panels. We've got some photos of that later on, but we've also got the patent pending. That's been a long and onerous process, so that's complete. And we are in manufacturing for the first validation structure for this development we're working with property service team on. So this is an optimized design where we're basically taking the interconnectivity and reducing it to precisely what is needed for this application, trying to really make it lean and efficient. So that's actually being built right now. Next slide. So this is kind of a top level summary of the system. As I mentioned, it's a bolt together modular system. So we can currently fabricate up to 16-foot tall panels that are 12 inches thick and up to 4 feet wide. And so that's, there are other manufacturers of similar systems in the market. Ours is unique in that it does not require the foam to maintain structural integrity. So a lot of similar systems that utilize foam and other structural components, if you take the foam away or break the joint between the foam and the other stuff, you lose structural integrity. We've actually done the load testing on our system without any foam at all. So that's a key design feature of our system, and that the insulation is not required to maintain integrity. Next slide. Let's see. Either next.
Sorry, I was on mute talking into the ether. Yes, so I just wanted to go ahead and say, as always, everybody, I've said in the chat box, but this is for everyone's mutual benefit. So you can post questions in the chat line. If you do have a question, if you'd like to raise your hand to be acknowledged, you may. Otherwise, you can just take yourself off mute and fire away. However, if you don't mind, Mr. Brady, I'd like to start with a question, if I may.
Absolutely, go ahead.
So I see R50. What is kind of like the standard R value of a wall, say the average of a wall in Fairbanks, Alaska?
Well, I guess that depends on the era of construction. Like current building codes, and there may be others that are more experienced in this matter, but R38 is fairly standard for a high performance wall system. In this climate, there are other higher performance wall systems, but the attention to detail required to really get to that level of performance, it's a pretty steep labor burden, and in those types of systems, the details of construction really make a big difference in the performance. And I think, yeah, I know Mike's a builder, he could attest to this, but the devil's in the details, and a lot of, there's a lot of ways to do it wrong and fewer ways to do it correctly.
So, but that much, if R38 is high performance, this is but that much more high performing.
Yeah. So one of the features in that insulation, basically, this is a 12-inch thick block of foam, and the steel elements in the system are thermally broken. There's been great pains in the design to maintain a thermal break between the steel elements on the inside and the outside of the frame. So, and those are tied together with a fiber reinforced plastic composite tie that we just took receipt of 10,000 of for this first phase of development. One thing I would add is that R50 value is based on a standard fire retardant EPS material. There is a relatively new product in the market that we are able to utilize that's a graphite modified EPS that has a higher R value. So in that same 12-inch panel thickness, we're able to get to R60 using that material.
Right on. Okay, so, thank you, sir.
Yep, next slide. So one of the kind of features of the system, recognizing the need and the shortage that we're all struggling with on the housing side, and if anybody here's an employer, you can attest to this as well, is there is not a lot of labor available at all anywhere for anything. So the design of the Arctic Lights system is really focused on being able to utilize automated assembly techniques. We can obviously, right now, we're doing it more manually during the initial phase, but as we move forward, we've worked with tooling and automation vendors to be able to take the framework, basically roboticize the framework assembly. And so that's really the key to being able to deliver this on the manufacturing side with the least amount of labor input available, and to get the consistency required for what is a structural system. So Next slide.
And if anyone would like this presentation, I do have it. Again, there's a lot of information that baked into these slides. Because I am seeing things like corrosion resistant, non-combustible, recyclable, steel frame.
Yeah, and I'm
water absorbent.
Rather than reading the PowerPoint,
oh no, it's fine.
Thank you for the steel framework. This is using galvanized steel. The materials of construction of the panels are themselves not novel. EPS foam has been around for over 50 years, and light gauge steel is light gauge steel. So these are two easily available commodities that have a long history of utilization in construction. So it's not necessarily a new technology, aside from the sense of how we have combined them and the interconnectivity. So EPS foam, there's a lot of different types of insulation material, each with their relative advantages and disadvantages. We selected EPS foam, even though we could have used other types of insulation, primarily for its stability, insulative properties, how it integrates with the system, how the framework can be encased, and I wouldn't say it's not relatively simple equipment because it does require quite a bit of plant, but it's one of the key features of EPS is that it's stable R value over its entire life. Some of the other types of composite foams actually lose ground over their life. So that's, once it's an R50 or R60 right at the outset, in 10, 20, 30 years, it's still the same value. So that's a feature as well that led us to EPS itself. Next slide, please. All right. So here we've got some of the kind of the structural design criteria, and we've done the testing. You can see some of the framework there and pictured, and that's some of the initial testing we had done, where we had done shear racking and axial loading. So we were able to demonstrate what would be the equivalent of 75 PSF over a 40-foot truss span, carrying floor loads with an equivalent 120 mile per hour design wind load. What's also not shown is for the tall wall project we were working on for a large commercial retail. Their structural requirements, we had built panels and tested for that project with a 720 pound per lineal foot shear racking resistance on a 24-foot tall wall. And this was all done without sheathing. So that was basically the steel framework encased in foam, resisting that load with no failure. So yeah, that's we're pretty proud of that. So, and it validated our application for being able to do larger structures. Not that that's going to be helpful for residential, but there certainly seems to be a significant demand in the market for enclosed shop space. So we're excited to further develop that variation on our design. And again, everything with R50 or greater. We've also, part of the design is integrating the roof system into the design because of the nature of how the connections occur. This includes the roof structure. So all of the roof system and structure are included in basically the baseline design, and it utilizes a cold roof, exclusively cold roof design, where the baseline panel insulation is 50 plus, and you can add supplemental blown-in insulation based on the economics of whichever project you're working on, to be able to get to 75, 90 or up, just based on how much more loose fill you put on top of the basic panel in a ceiling. So All right, next slide. So this is kind of the secret sauce of the system, and this is some of the earlier, we've gone through to date 13 design revisions, and there are more to go, but the basic structural connections are made using a 3/8 bolt and a handheld impact driver. And there's a panel gasket that is provided with the system that goes between the panels. It's basically a 12-inch wide strip of sill seal. So it forms a pretty robust gasket when compressed at a pretty significant bolt joint torque to squeeze the panels together to eliminate air leakage and allow for, that's the rapid field connection, where you bring the panels together and basically tighten them with the bolts at each corners. And depending on the size of the panel, there may be intermediate bolt connections as well. So, so pictured are some of, I think that's the Rev 11 design. The other kind of interesting feature on the bottom right and middle are how structural connectors for things like floor joists or the trusses themselves connect to the wall panels. And this is applicable as well to alternative foundations like raised post and pad construction as opposed to slab on grade. But there's a part of the design includes the ability to connect structural knife plate between panels that are actually done without supplemental fasteners. So that picture of the flat truss joists in that is actually assembled without any hardware. So no screws or bolts holding that together. And we were able to structurally test that in that pictured configuration. And it's a very, very robust connection that went together basically as easily as setting a joist in a joist hanger. So that's part of the innovation of the system, is really how it connects. All right. Any questions so far?
Yes, any questions so far? All right. If not, that's fine. Again, I'm monitoring both the participant list and the chat box. If you have a question, you can post it in the chat, throw up your hand, or just take yourself off mute. And again, we'll have these slides available, so when we get to the end, if you want to refer back to anything.
All right. And next slide, please. So this is kind of a top level overview of the panel configurations. And again, this was one of the revisions that's approaching the ability to take a standard off-the-shelf collection of panels that are all designed to bolt together on standard dimensions and be able to utilize them to get effectively custom construction. So that's the sort of, we've taken a different approach to modular. Instead of sending a shop drawing in for your play, or sending your plans in, a shop drawing being generated, and then an entire wall cassette being built, which that workflow often takes months. The approach we took is the ability to build standard panels that can be stocked and then mixed and matched to achieve different size openings, different wall configurations, whatever plan variations you need can be made real by utilizing standard components. So that's the sort of modular generic approach for larger scale developments, like the one that we're just beginning to work with local developer on, where it's a bunch of copies of a similar design. We're able to basically make that custom plan to really dial in labor to the greatest extent possible and make the same quality construction as efficiently delivered as we can, since we don't need the full modular functionality for that application. We can customize it to suit exactly what's needed. So these are just kind of some of the, headers and how things can be put together. So you can see some of the pieces go together to form what would be a custom wall stack with a couple different size windows and a door open. So that's just kind of a baseline sense. See, I see a testing panel filled with foam when we tested the 720. That it was, but we did the same test without foam. So we actually tested the frames in that high shear application. And we did that to kind of observe some of the deformation of the elements, and that 720 PLF on that application was I think I might have a picture of that in later deck, but go ahead, next slide. So this is kind of the system, as I mentioned, can be utilized on any type of foundation. Where it can bolt directly to a concrete slab. For a slab on grade, it could be set on a stem wall made out of ICFs or other types of construction, and also what might be alternative post pad type foundation, such as a triodetic or any of the other systems. So we're agnostic and able to bolt to any type of structural element. And so the big one we're working on, obviously, if the soils are good, utilizing the thermal mass of a slab, where we can screw the panels directly down to the concrete, as opposed to building a floor out of the panels up raised off of the ground. So, and again, utilizing the flat joist type construction that connects to the panels, we're able to do multi-story construction, utilizing the system entirely, all without, we haven't gotten to any wood or screws at this point yet in this construction.
I just quipped to my in-room guests. So I have a single-story home, cinder block construction. Almost makes me want to put another level on my house.
Yep, could be done. We have not yet. We've had some inquiries on utilizing the Arctic Light system in renovations, and that's one of the kind of interesting features of this system, is that because it's bolt together, it can be unbolted. So it lends itself to the possibility of rapidly deployable portable structures that can be, assembled and then disassembled and laid back down. Obviously, you're not going to do that with a house, but applying it to a renovation application, we have not yet detailed that, but it's one of those, because we can connect to nearly anything, the ability to add on or modify existing structures, or even modify the Arctic Light structure itself downstream, remains a possibility. So next step, or next slide.
Okay.
So you'd seen kind of the highlights of where we are. We actually have our pilot plant out in Fox. We're manufacturing the frames in town at Sun Air Sheet Metal, and we're manufacturing the EPS foam. Part of the process is out in Fox. And that plant is now functional, and we're foaming panels, and we're just taking our first steps into the commercial market with this development that we're excited to be working with the property service team on. Some of the next steps as we continue to push the technology forward are third-party testing. For certain jurisdictions, that's going to be required. We've actually, because we're utilizing UL listed materials throughout, and doing fire resistant construction, utilizing stuff that's already listed for building applications. We're good there, but as we start looking into more federally funded projects, that third-party ICC certification is going to be required. So that's in terms of next steps. And then doing the offsite, we've done our own we've done our own structural testing, but we have not yet sent that off to a third-party test lab. So those are, that's a heavier lift in terms of getting that validation done, but we've satisfied ourselves that it exceeds all performance requirements from a life safety structural perspective. So these are some of the things that we've got on our docket for expanding the applicability of this technology. Next slide.
Oh, we do have a question in the chat box. Can you clarify the weight of the wall panels compared to equivalent wood framed structures at a similar R value?
So good question. I haven't gone out and done the weight analysis on the wood frame component, but for us to get to a fully completed wall panel, a single panel for 8-foot finished ceiling, single story construction that's optimized, that panel would be somewhere around 100 to 105 pounds for effectively a 9-foot tall panel. And that's using, we're using 1.2 PCF density foam. So the weight of the steel in the panel versus the weight of the foam is roughly comparable. So fairly lightweight, something 2 people can carry around a 4-foot wall panel section. So they're slightly lighter than a SIP as well. Actually, a fair bit lighter than a SIP. So because we're the weight of the studs relative to a wood stud to a metal stud, I think the metal studs are lighter. Our system doesn't require sheathing. Insulation is a little bit heavier, but it's something that's already done and integral to the panel. So, and then to get to a R50 wall, you're going to you will require R50 wall made out of wood generally is a double offset wall construction with 2 layers of sheathing. So it will be heavier even without the insulation. So, all right, next slide.
Sure. Good question.
So, yeah, that's kind of the other thing in terms of we've had inquiries from architects and structural designers. So far, in terms of taking this product and making it applicable, to like your architect to design your building. We're working with some architects directly, but that's in the next steps to develop basically the installation manual, all of the load tables and design guidelines. And the inspector's manual, we kind of referenced that. We had made a presentation of this system to the local building officials here some months back. And it was an interesting discussion relating to how, the inspection requirements on residential construction, you're going to have certain features of this type of construction utilizing our panels that are inspected very differently. So we've educated the local building officials on our product and kind of started the dialogue on how to do what would be anchor testing or framing inspections or, any of those types of things that you would traditionally see. Those will be a different process utilizing our system. And it simplifies it vastly in the sense of being able to assure the delivery of quality construction in that, if the bolt is in the socket and tightened, it's there, it's done. So it's a very simple visual inspection of a very small number of points within the system to be able to verify that it was installed correctly. So, and this is kind of key to being able to utilize less skilled labor to assemble. So these panels do not require a great deal of skill to assemble. And that's really part of the key, given the labor shortage on skilled construction labor, this was a way to take the same skill. You're not going to get rid of skilled labor, but to be able to either accelerate delivery using the same amount of labor, or to be able to utilize less skilled labor to get to residential structures. So part of that is making sure that it can be done safely and efficiently. So that's kind of all of this is woven into that effort. Next slide.
Well, let's see. We do have one question quickly in the chat box. Is a hold down insulation internal, or is hold down insulation internal to the panel?
Yes. So the panels attached to the structure and to the trusses. So what would be your Simpson ties or J bolts? We're recommending it'd be like a Simpson or Hilti concrete screw. These are seismically rated. So a 3/8 by 2.5 screw that you would drill into a slab on grade or bolt to another foundation element, but that bolt joint is internal to the panel. So there's nothing projecting out past the face of the panel. And so finishing the panels is very easy because you don't have lumps for connectors sticking out past the face of the surface. And you don't have what would be the equivalent of hurricane ties, because the load path from the foundation all the way up is through the integral panel frame that is all bolted together. So, and yeah, all internal to the panel. So it requires either a U joint or a right angle adapter to be able to get to the bolt heads. Or, you can do it with a regular socket wrench as well manually, but yeah, nothing sticking out, no track, no external clips or external fasteners. Next slide. So this is kind of the last step. As I mentioned, we're working with a local developer on a much needed development, using our technology to help them accelerate delivery. So that's, we're actually in fabrication on that structure as we speak. And we're hoping to get assembled in their shop before the end of the year. And that's going to be kind of the template that we'll use to move forward with their development. And this is going to be, this whole project, as I mentioned, was conceived in response to the DOD-driven housing shortage. And we're excited to be working with this developer to finally make real the promise of bringing something to market that's affordable and will provide much needed, targeted right at that BAH market. So yeah, it's been a great partnership thus far, and we're excited to work with them to really help them move their effort forward using our technology. And I think we're close to the end. Yep.
Yes.
So there we go. So that's, and I think we've got the developer online, Marshall, if you wanted to speak to his, but that, I think, as Jomo mentioned, they've been working with the EDC separately. And so we're, like I said, real grateful to be working with them to be able to bring this to market. That's, it's anybody that's been around since the pipeline remembers, some of to Jomo's question about what's the R value of a typical wall around here. Well, some of the structures that were built back in those days during the last boom were not the greatest construction quality. And so we're saddled with that high energy burden in the market right now for kind of substandard construction. The these are, you know, being able to work with a developer to deliver what would be high quality, high performance housing affordably is, you know, something that I'm pretty proud about, given that the easy temptations to do something inferior. So we're past the codes on this. See a question, avoid infestation from critters like carpenter ants. So there's nothing in the panels that is food, for starters. So no wood, and the foam is not nutritious, but they can, you know, it'd be any of the standard ant pest prevention measures, the boric acid around the foundation sorts of details, but nothing in the panels itself is tasty, like, you know, plywood and porcupines, or 2x4s and, you know, potential dry rot and infestation of carpenter ants. So that's the answer to that. Backing included or added? Absolutely yes. So, and this is where, because of the light gauge steel construction and the way the panels are assembled, it looks almost more like commercial construction in how you do backing. We can either, for this project in particular, we're coordinating the backing in the walls to line up with other, you know, things like cabinets. And prior, you know, and if barring that, you can actually lay down, you know, screw a strip of flat metal to the exposed metal surfaces of the panel prior to sheetrock, and that's usually enough to do cabinet backing as well. And then electrical conduit be embedded in the panels. That's one of the design evolutions that we are moving forward with. Short answer is yes, it can be. And we've looked at ways to do that. And right now, the current sort of electrical rough-in methodology for this system is to hot knife cut the exterior surface. Is all of the framing on the outside is 1.5 inches thick. So to be able to run, you can hot knife cut a channel 1.5 inches deep, all the way through the face of the panel, and cut your boxes into the solid block of foam, you know, for a field installation. But and so you don't need nail shields, because you can push the conductors back into the panel far enough. And unlike SIPs, you don't have to fish, you know, the cutting, there's nothing to compromise the structural integrity of the panel by cutting through the plane of the surface of it, because again, the foam is not structural. So doing electrical rough-ins on this system are relatively straightforward, in that you don't have to fish wiring, nor do you have to fight through a layer of sheathing to get to a raceway. All right, any other questions?
Yeah, I do see Mike Music has his hand up. Mike.
Yeah, thank you. Thanks, Glenn. I know you make good beer, so I think.
Yeah, we've just integrated our foamy. It's a foam, all things foamy is what we're doing.
There we go. I've done a lot of blow dryer testing on SIP homes, and they're similar in terms of structure, it seems, where you butt panels side by side or top and bottom.
Yep.
And I always found leakage there. And I also found leakage at wall outlets, because typically the electrician would bring the wiring through the floor system, which when you got out to the rim joist area was leaky. So I think those details need to be quite explicitly outlined for the electricians and for the plumbers, because airtightness, once you got the thermal value there, the R value rather, it's the air tightness that makes the difference in terms of whether you've got a good home or not.
Yep,
So
absolutely.
those details, I think, need to be really clearly explained to your subs, the trades that follow the framers.
Yep, absolutely. And then that's something that looking at, how other types of panelized systems connected, SIPs, or as you're familiar with, are often using splines and sealant. Um, and we, and it's somewhat cumbersome and complex, particularly if you're out in the field and it's cold and rainy. It's less than ideal. Um, the the gasketing we use, the interpanel gasketing, is a 1/4 inch thick EPE material. So it's so it's basically thick seal that is the entire width of the panel that gets compressed both all the way through the thickness. So it's a 12-inch compressed gasket. And we'd looked at the physics of compressing that gasket. It actually goes from a 1/4 inch to an 1/8 inch, and it takes up about, on a typical wall panel, about 9 feet high. It's about a 800-pound squeeze to do that. So it can't actually be done using anything other than tightening a bolt. So it's a pretty robust. We actually had explored camlock technology early on, but it was not robust enough to compress that gasket. So
Do you have a structure you've done the blow door testing in to
we
verify
have
that?
not. We actually are looking forward to doing that test here, hopefully before the end of the month, on that first. So short answer is no, but in terms of the question about the vapor barrier of the system, because of the Mike, what you had mentioned, those details, certainly electrical box sealing is a big part. And we're looking at some of the details on how electrical rough-in occurs, where it may be better utilized through the ceiling instead of through the floor, but those are kind of up to the individual builder. And yeah, absolutely getting the air barrier controls correct. For the vapor barrier for this system, that's one of the other reasons we chose EPS material, because it itself is actually quite porous, and it breathes, and water vapor can permeate through it relatively readily. So this system does require a vapor barrier, and what we're applying on this is a liquid spray applied vapor barrier that would occur after electrical rough-in. So the entire structure is enclosed, and the electrical rough-in, all the channels are cut, boxes are in. Because it's a solid block of foam, at that point, we're trying to provide that vapor seal surface. So it's, liquid spray applied vapor barrier prior to drywall application or exterior finish application. So in terms of the blower door testing, and there's inevitable little leaks. That's what we're really looking forward to getting down to. The panels themselves are going to be great. Compressing the gasket, and with a SIP, I don't believe there's a way to, short of building cleats in to be able to pull the panels together. You're relying on the sealant and the screw joints to maintain the integrity of the system through that spline joint at the panel edges. So because ours are bolted, we can, like I said, really squeeze that gasket between the panels. So we're looking forward to, we're going to be paying close attention to panel corners, and some of those sorts of details, but how the gasketing and the vapor and air barrier, in addition to the thermal barrier, that was actually, I think, the first 7 revisions of the design were a lot of trying to optimize the interconnectivity and getting things to seal. And we have bolted lots of panels together, but we have yet to form like a fully testable structure. Like I said, that's coming here hopefully in about 2 weeks. So, once the home's dried in without a vapor barrier, how easy? So that's another great question, is because the EPS is breathable and there's nothing in this system that is subject to degradation by water or moisture. Once the structure is enclosed and dried in, you can temp heat it even with direct fired natural gas, where you wouldn't want to try that on normal construction where you've got a moisture loading inside a structure that's driving through your insulation system in the winter. Any moisture that does make its way into the wall panels during construction will find its way out. So for this system, we actually do not recommend house wrap. So an exterior water infiltration barrier, because the foam itself is water repellent, but vapor permeable. So that's being able to get a structure enclosed very easily and be able to temp heat it and then do finish inside a structure that you can, hack holes in, and you don't have to worry about the system kind of falling apart during construction if you're going to extend the season into cold weather. So that's one of the advantages of this system, as well as being able to extend the season and enclose things rapidly, that so that interior finish can occur off peak. You're less constrained by the building season because of the utility of the system.
Rick, I see your hands up. Mr. Soley, please.
It is. Thank you, Jomo. Glenn, fascinating presentation. Have been out to the shop there at Goldstream and looked at your manufacturing site, and very impressive. And the discussion you just had is above my understanding, but I trust that folks have looked through the design and the perfecting it as you move through the process, and you're at patenting now. My questions come more on the financial, economic side and market acceptance. Can you talk a little bit about where you are as far as being able to bring this product to, say, Spenard builders, and how that price point would compete with products? And obviously you address the worker piece, that is, a person could consider the lower cost of skilled labor needed, and so that would factor into capital comparison. But can you talk about that a little bit, just access to capital, pricing, and those things, if that's appropriate at this time? Thanks.
Yeah, so on the pricing side, we had done an analysis, kind of trying to do the best apples to apples comparison we could make on the Arctic Light system relative to SIPs and relative to conventional stick built, but done at an R50 performance level. And so to do a R50 SIP, typically the wall panels are not available. You'd have to use what are normally a roof panel for a wall panel, and foam is foam. So you're, regardless of what type of construction you're using to contain that much insulation, you're going to end up with a 10 to 12 inch wall. And to get the thermal performance, you've got to really eliminate thermal bridging to the greatest extent possible. So SIPs, that's kind of built into the system. Ours is built in, even though the steel framework, steel conducts heat extremely well. It's the composite plastic ties between the inside and outside frames provide the break. And so we've done the composite analysis of the bridged system. And so, when you put sheetrock and some siding on it and trap a tiny bit more air, that's where we get 50. But to do in terms of cost, our materials are obviously, well, they're more per square foot of wall on the material than it would be. You could go down to the store and buy all the parts to do a double stud wall, and including the sheathing, at pretty high prices, not even COVID prices, but after things have kind of come back down in the lumber market, the materials of construction to get an R50 stick built are substantially cheaper, but when you factor in the labor, we beat stick built construction. As our best guess is we're about 35% cheaper than equivalent performance stick built on a apples to apples basis. And a SIP, we're about depends on how skilled the assembler is, 20 to 25% cheaper than a SIP. And to get R50 to a SIP, you've got to do a little bit more to it. And there are some disadvantages of SIPs we feel in the Arctic climate relating to moisture migration challenges. So the real advantage on the cost of our system is that it is the labor, or the significant reduction in labor to get to high quality construction. So to get R50, assembling SIPs takes a bit of skill to do properly, as Mike mentioned, and there are lots of difficulties. Assembling an R50 stick built wall is a non-trivial exercise. That takes somebody who knows what they're doing. And especially in the details of construction. So we're basically cheaper, faster, and better. And so we were pretty happy with that analysis. In terms of the capital piece, that's something we're still cracking that nut, but we're confident we're there. We've got some things in the works that were helping us get the resources to bring this to the commercial market that we're looking forward to being able to share, hopefully in the next month. So
thank you, Glenn. Really exciting and encouraging. So thanks much.
Yeah, appreciate it. Let's see, a question: expected time frame to dry in a 1,200 square foot home using this system. So from the slab ready to set panels on should be for a 1,200 square foot, which would be like a 3-bedroom, 2-bath, 1-car garage type structure. We're anticipating the whole thing could be dried in, including the roof trusses, like dried in, ready to take weather and be heated within 3 days with 2 to 3 people.
That's fast.
And it's because it's basically as fast as you can stand the panels, tack the gasket to the edges, and bolt things down. And then once you've got the panels assembled, you just keep moving to the next panel and start stacking them up. The structure and the thermal envelope are going together, at the same time. So it's, once the last, panels bolted together, it's ready to heat immediately. All right.
Well, Glenn, I've been wanting this presentation for a while. When you let me know you were finally ready, I jumped on it. So thank you so much. We are nearing the very top of the hour. I would, property service team, Marshall, you've been posting things in the chat box, but I didn't know if you wanted to take just one moment.
Sure. Our involvement with Glenn started not that long ago, but I was in the development that we have planned and have worked with the EDC on some approvals and modifying our system to work well inside of the borough. Through the course of that, we ran into Glenn, and this system speaks to a lot of the challenges of doing things at scale, which we had planned, but we had the typical pre-manufactured wall framing jig systems that don't really change how a home's built. It's just the same thing. It just kind of creates some efficiencies, but we're still building a home the way we've built homes for over 100 years. And that style doesn't lend itself well in the Arctic environment. We have to do a lot of things that are not typical in the States, as everybody knows, to make the thing work here and actually to have decent R values. I know Glenn spoke a lot on the challenges of actually achieving an effective R value in a wall system in Alaska that provides energy savings. You can spend a lot of money insulating a wall with typical methods, and if it's not done at a supreme quality, it's wasted money because you have problems with air leakages, you have cold spots, you lose the effective R value of a wall when it's not done expertly with traditional methods. So the part that really intrigued us was the shortened building season that exists in Alaska, the effective R value of the wall panel system when it's all bolted together properly is such a great return on the energy investment over time. And energy prices may not go down, in the long term. I think maybe eventually when we get better energy supply, prices may come down, but that's not going to be anytime soon. And so with the wall panel system that Glenn has developed with Mark, the return on the upfront investment, it seems more valuable than any other wall panel system that I've explored and looked into. And I love trying to build in efficiencies and solve problems and eliminate bottlenecks. And this system kind of hits a lot of those key components. And that's why we're really excited about continuing a relationship with Glenn. And I know he stated we're in the actual manufacturing process of the panels with Glenn right now, and we hope to have enough panels produced to start erecting a building inside of a warehouse that we own. And we're very interested in allowing people to come do walkthroughs and actually experience this thing in real life. I'm a very much hands-on person. PowerPoints are great. The drawings and the engineering that Glenn does is amazing. It's not real to me until I can touch it. How do these panels go together? How difficult is it? How do we actually connect it to a concrete structure? How well does that work? What does the blower door test say when we're done with this? What modifications can we make to improve and adapt the system to fit the Arctic environment? And I'm amazed at the stuff that Glenn has worked out in the engineering realm. Some of these things seem somewhat obvious, like a frame structure that stands on its own and is not reliant on a material that degrades over time, like OSB in a SIP panel situation, and or what happens if in installation there's racking that maybe pops the insulation loose from the steel structure itself. In other systems, your system now has a failure point. And so it seems incredibly obvious to well, why can't we just build a frame structure that is the engineering load carrying device? And the fact that Glenn put that together is just amazing. And it seems so incredibly obvious after it's done. So I think there's a lot of advantages that Glenn and his team have put together that I think will play out very well into the very near future in what this panel can do, not just in the Arctic environment, but in a lot of challenging environments, areas where ground is hard to build on, areas where there's a constant need to be heating the thing like from the day of the beginning of construction. I don't know how many people have seen, these bubbled tents that people set up to build a building here in Fairbanks, and I've had to do it myself a couple times. And boy, if you're not burning 1,000 gallons of fuel a day, it gets real expensive real quick. So anyways, I could go on for a long time about what the perceived advantages of this system are, but we're really excited to be working with Glenn to prove out this concept and to invite people that are interested to come see the thing as it exists in the real world. Our target is before the end of year, but we are running into holiday seasons, and being with families super important to us as well. So we may not hit that target, but we're pushing real hard to do so, not at the expense of spending time with friends and family during the holidays.
Oh, it's fine. We might plan for a spring field trip. I've been threatening to take these guys on field trips for years. So,
It would be
it's been a
wonderful.
while since we did one. And actually, Miss Slava just saw the facility. She did a tour just yesterday, if I'm not mistaken.
That's great.
All right. Well, thank you, sir. Mr. Brady, thank you. And Mr. Sherman, it's good to see you, your name online. So everybody, yeah, this was awesome. So we'll be keeping tabs as we have been, and wishing you all success, and looking forward to when we can actually, go not kick tires, but with little pats and panels. Okay, so I did not have anything fully scheduled for next week. I did see in the news that that energy plan has come out. Thank you for your reporting, Jake. And so, or Jack, we will, I was going to maybe reach out to AEA or whomever to see if we could get a briefing on that plan. But otherwise, I thought I would give everybody the rest of the holiday season off. So yeah, everybody, again, Mr. Brady, Mr. Marshall, Mr. Sherman, everybody, thank you so much for joining us. Happy Hanukkah for all of us who celebrate. Merry Christmas coming. So happy holiday season. And again, I will let you guys know if we're having a meeting next week or if we're just kind of, again, we're good for 2023. Otherwise, everybody just have a good day, good rest of your week, safe and happy holiday season.